are relevant to enterprise networks. After completing this lesson, you should be able to achieve the objectives shown on this slide. By demonstrating competence in routing, you will be able to describe how FortiGate routes traffic, diagnose routing problems caused by reverse path forwarding check, identify sessions that will be routed through a different path, and use debug commands to troubleshoot routing problems. In this section, you will learn about general routing concepts and troubleshooting. A FortiGate is a stateful device, so it decodes a lot of information at the beginning of a session based on the first packets. For any traffic session, FortiGate usually performs only two routing lookups, one on the first packet sent by the originator and another one on the first reply packet coming from the responder. After that, all the routing information is written in the FortiGate session table. However, after a change to the routing table, the route information is flushed from the affected entries in the session table. So FortiGate would perform additional routing table lookups in order to repopulate the session table with the new routing information. How does FortiGate decide routes? FortiGate has multiple routing modules. The diagram shown on this slide illustrates the logic of the routing modules. First, FortiGate searches its policy routes. You can view them using the command diagnose firewall proute list. If there is a match in a policy route and the action is forward traffic, FortiGate routes the packet accordingly. If the action is stop policy routing, FortiGate goes to the next table, which is the route cache. You can view that content using the CLI command diagnose IP RT cache list. Finally, FortiGate searches the forwarding information base, FIB. The FIB is generated by the routing process and is the table used for packet forwarding. Think of the routing table's purpose as management, while the FIB's purpose is forwarding. This separation becomes clearer in FortiGate Active High Availability HA cluster. In an HA cluster, both route management and forwarding tables exist on the master FortiGate. But on the slave FortiGate, only the FIB exists. If there is no match in any of those tables, FortiGate drops the packet because it is unroutable. When there is more than one route to a destination, this is the process for selecting which route to use. First, FortiGate uses the most specific route, which is the one with the longest net mask, smallest subnet. If there are two or more routes with the same longest net mask, the unit selects the one with the shortest distance. After that, the lowest metric is used as the tiebreaker for dynamic routes. In the case of static routes, the priority is used instead. If there are multiple routes with the same net mask, distance, metric, and priority, FortiGate shares the traffic among all of them. This is called Equal Cost Multipath, ECMP. ECMP is supported for static, BGP, and OSPF routes. FortiGate adds a static route to the routing table only if all of the following requirements are met. The outgoing interface is up. There is no other route to the same destination with a shorter distance. The link health monitor, if configured, is up. Now you will review an important routing concept, reverse path forwarding, RPF check. RPF check protects against IP spoofing attacks and routing loops by checking the route to the source IP address. This check is performed only on the first packet when the session is being created. If the check fails, the packet is dropped and the debug flow shows this error: reverse path check fail drop. There are two RPF check modes: feasible path, formerly known as loose, and strict. Feasible path is the default mode. In feasible path mode, the packet is accepted as long as there is one active route to the source IP through the incoming interface. It does not have to be the best route, just an active one. In the example shown on this slide, the packet from 10.4.0.1 to 10.1.0.1 is accepted because FortiGate has an active route, the default route to 10.4.0.1 through port 2. However, the packet from 172.16.1.1 to 10.1.0.1 is not accepted because there is no active route to the IP address 172.16.1.1 through port 3. In strict mode, FortiGate checks that the best route to the source IP address is through the incoming interface. The route not only has to be active, as in the case of feasible path mode, but it also has to be the best. If you use the same example, but change FortiGate from feasible path mode to strict mode, you will get the following results. The packet from 172.16.1.1 to 10.1.0.1 is still blocked because there is no route to the source IP address through port 3. The packet from 10.4.0.1 to 10.1.0.1 is also blocked. There is an active route to 10.4.0.1 through port 2, but it is not the best route to the source IP address. The best route to 10.4.0.1 is through port 3. So strict mode accepts traffic from the subnet 10.4.0.0/24 only when port 3 is the incoming interface. Content inspection requires to keep routing as symmetric as possible. That is, traffic must follow the same path both ways. There are multiple scenarios where asymmetric routing prevents FortiGate to inspect traffic content. So FortiGate routes traffic symmetrically. This means that under some network topologies, FortiGate might not route the return traffic from the best path, but through the same path that the originating traffic used. For that purpose, FortiGate remembers the interface to source and uses that interface to route the return packets, even when a better route using a different interface exists. You will look at an example in the next slides. Now you will analyze this network topology. The local network 10.1.0.0/24 has 3 network devices, a local workstation, a local router, and a FortiGate, port 1. Also, the FortiGate port 2 is directly connected to the local router using the subnet 10.2.0.0/24. There is a remote router connected to FortiGate port 3, and behind that, a remote server, 10.4.0.1. So any traffic destined to the remote server must be routed through the FortiGate. One important detail in this network is that the local workstation default gateway is 10.1.0.254. This means that if you send an ICMP echo request from the local workstation to the remote server, the packet goes to the local router first, then to the FortiGate, then to the remote router, and finally to the destination. When the ICMP packet arrives at the FortiGate, an entry for the originating traffic is created in the unit route cache. This entry contains the interface to source, or the incoming interface where the packet arrived, which in this case is port 2. Additionally, FortiGate creates an entry in the session table. This entry also contains information about the interface to source. As explained earlier, FortiGate does a first routing lookup to find the next hop to the destination. That IP address is also stored in the session information. Because there is no ICMP echo reply yet, you will notice that the next hop to source is still unknown. It is 0.0.0.0. It will be identified with the second routing lookup that happens with the first reply packet. Now take a look at how FortiGate routes the return packet. When FortiGate receives the ICMP echo reply, because there is already a session and a route cache created, it uses the interface to source. So in this case, the unit routes the packet through port 2 toward the local router, even when there is a better route to the destination, 10.1.0.1. The FortiGate routing table shows port 1 as the best route to 10.1.0.1, locally connected, but it still uses port 2. The objective is to keep the traffic flow symmetric. With the first ICMP echo reply, a second entry is added to the route cache, this time for the return traffic. Additionally, the unit does a second routing lookup, this time to find the next hop or gateway to the source. That IP address is added to the session, which was previously set to 0.0.0.0. What happens if the traffic originates from the server side instead? Say that the ping is sent from the remote server to the local workstation. In this case, when the ICMP echo request arrives at FortiGate, there is no session yet. So FortiGate uses the best route to 10.1.0.1, which is through port 1. This example shows how FortiGate might, in some network topologies, route packets to the same destination differently, depending on who initiated the session. Take a look at the reply traffic in this example. Because the local workstation default gateway is 10.1.0.254, the ICMP echo reply goes to the local router first. Then, the packet arrives at FortiGate port 2. The result is asymmetric routing. The return traffic is following a different path than the originating traffic. The return packet is arriving at port 2 instead of port 1, where the originating traffic was sent. In these particular cases, FortiGate accepts this asymmetry, no packets are dropped, and security inspection is not affected. When FortiGate is not applying SNAT, after a change in the routing table, the routing information is removed from the sessions that are affected by the change. Additionally, related route cache entries are deleted. So 2 more routing lookups are done for the next packets in order to learn the new routing information and store it in the routing table. This slide shows a sample of a session just after a routing change. The gateways in both directions change to 0.0.0.0/0 and the interfaces to 0, indicating that this information must be learned again. Additionally, the dirty flag is added. You can configure session route persistence at the interface level using the commands shown on the slide. The default value is disable. If you enable this setting, sessions passing through that interface will continue to pass without being affected by the routing changes. The routing changes will apply only to new sessions. In sessions where SNAT is applied, the action that FortiGate takes after a routing change depends on the SNAT route change setting. When the SNAT route change setting is disabled, the behavior that occurs after a routing change is different for sessions using SNAT. Sessions using SNAT keep using the same outbound interface as long as the old route is still active. In the example shown on the slide, FortiGate is connected to 2 different ISPs. A client with the IP address 10.1.0.1/24 is connected behind a FortiGate. FortiGate is doing SNAT of the client traffic to a public IP address, depending on which ISP is using it. The FortiGate routing table contains 2 default routes, one for each ISP. The 2 default routes are the same distance but have different priorities. The route with the lowest priority, port 1, is the primary. When both ISP connections are up, the primary route is selected by FortiGate for Internet traffic. So all sessions to the Internet are created using port 1 as the outbound interface. If you increase the priority assigned to port 1 to a value that is higher than the value assigned to port 2, and if SNAT route change is disabled, all new sessions start using port 2 because it has the lowest priority. However, all the existing sessions continue to use port 1. The default route is through port 1. Even though the default route is no longer the best route, it is still active. If FortiGate is doing SNAT, the existing sessions will continue to use the original route until they expire. If FortiGate isn't doing SNAT, all the existing sessions will switch to port 2 after the change. When SNAT route change is enabled, after a routing change, the actions are the same as they are for sessions without SNAT. Routing information is flushed from the session table. Route cache entries are removed. Routing lookups are done again for the next packets, which can potentially change the outbound interface being used to route the traffic. RPF check is done again for the first packet in the original direction. In the example shown on this slide, FortiGate is connected to two different ISPs. A client with the IP address 10.1.0.1/24 is connected behind a FortiGate device. The FortiGate routing table contains two default routes, one for each ISP. The two default routes are the same distance, but have different priorities. The route with the lowest priority, port 1, is the primary. When both ISP connections are up, the primary route is selected by FortiGate for Internet traffic. So all sessions to the Internet are created using port 1 as the outbound interface. The scenario shown in this slide has multiple ISPs. If the customer owns a pool of public IP addresses, the customer can configure a single IP pool for SNAT for all the Internet providers. The advantage is that if the main ISP goes down, sessions are routed through a secondary ISP, maintaining the same public source IP address. In this way, sessions can remain up. So, in the example shown on this slide, if you increase the priority for port 1 to a value higher than the priority for port 2, and if SNAT route change is enabled, after a routing change, routing information is flushed from existing SNAT sessions. All sessions start using port 2 because it has the lowest priority. Additionally, if the port 2 route shared a common IP pool with the old best route of port 1, the SNAT session will keep using the same public IP addresses for the translation of the private IP addresses. The command shown on this slide displays all the active routes in the routing table. The left column indicates the source for the route. The first number inside the square brackets is the distance, and the second number is the metric. This command doesn't show inactive routes. For example, if you had two static routes to the same destination subnet with different distances, the one with the shorter distance would be active, and the one with the longer distance would be inactive. If you entered this command, it would display only the active route. If you want to display both the active and the inactive routes, use the command shown on this slide. In the example shown in this slide, the output shows one inactive route. The route is inactive because it has a longer distance. This low-level command shows the FIB, which is the routing information that the kernel uses to route traffic. All active routes in the routing table must be present in the FIB. Additionally, the FIB may contain routes that are not in the routing table but were automatically added by FortiGate, such as routes that are dynamically added to reach SSL VPN users. The route cache contains recently used routing entries in a quick-to-search table. It is consulted before the routing table to speed up the routing lookup process. In this section, you will learn about virtual routing and forwarding. Virtual routing and forwarding, VRF, is a technology included in some routers that allows multiple instances of a routing table to exist in a router. This increases functionality by allowing network paths to be segmented without using multiple devices. Because traffic is automatically segregated, VRF also increases network security. Internet service providers often take advantage of VRFs to create separate VPNs for customers. This slide shows another example of a data center service provider. Using VRFs, the service provider achieves full Layer 3 path isolation. VRFs can include IPsec interfaces, so the routing isolation stretches all the way to the tunnel termination at the data center edge. This setup reduces the configuration complexity when compared to a similar solution you can achieve using VLANs. FortiGate supports Layer 3 routing isolation using VRFs. You can configure a VRF ID on an interface. A wide range of interfaces are supported, such as physical, VLAN, IPsec, switch, and aggregate interfaces. Interfaces with matching VRF IDs are isolated to a VRF instance. This slide shows the commands required to configure a VRF ID on an interface. The VRF ID is an integer between 0 and 31. OSPF is the only dynamic routing protocol that supports VRF. Neither BGP nor RIP support VRF. After you configure VRF IDs on interfaces, the routing table diagnostic command output changes. FortiGate groups routes based on VRF ID. From the routing table output shown on the slide, you can see that port 1 and port 3 are in the same VRF instance, VRF equal 1, and port 2 is segregated in a separate VRF instance, VRF equal 2. The routing table database output also changes. Both active and inactive routes are grouped based on their VRF instance. The route cache entries will also show VRF ID information for recently used route entries. This slide shows the objectives that you covered in this lesson.